proton number equals to 2, 3, and 4. What happens if we put them in increasing order? Well, they discovered what we call the periodic law. As the number of the protons increases, a certain set of properties recur periodically. So you go from metal to non-metal, and then once you reach the end, if you will, you come back to metal again, and going through the transition, go to non-metal again. And then this is how we try, when we try to put the elements in the increasing order of atomic numbers, number of protons there, we realize there is a recurring property, and that happens periodically. So we can use this pattern to make predictions. And in the 1800s and 1900s, early 1900s, we don't know as many elements as we know now. So there are a lot of elements that we don't even know at that point yet. But according to the arrangement of increasing proton number of the atoms there, we made some predictions there. And later on, the discovery of the new elements there proved that those predictions are pretty darn close to the prediction. So these are the examples there. So gallium and germanium, those were elements that we don't know at the time. So we made the prediction based on what we already know, to the left, to the right, in the periodic table. And then we make all these predictions there, and they came out in the discovery later on proves the prediction is pretty close to what's been predicted there. So what determines the property of an element? Well, in this chapter, we're going to look at what we call electron configuration. What are the repeating patterns of the electron distribution in the atoms of different elements there? And what we want you to be able to do, now that we know how the quantum numbers, we want you to be able to distribute those electrons to the atoms of any element in the periodic table, and be able to write out what we call electron configuration, okay, for the elements, and be able to predict their position in the periodic table, and from the electron configuration. So we're going to look at what we call electron configuration. How do we define electron configuration? Well, in talking about electron configuration, you have to go back to what we just talked about at the end of chapter 7, there, quantum numbers. To locate electrons, the arrangement of the electrons follows a particular set of rules. And then we have to know which shell they're in, n value. We have to know how many subshells we have in each shell, and then we have to know each orbital there. So when you look at electron configuration, well, by definition, electron configuration is the arrangement of electrons in the energy level and the subshell of an element there. It's also called spectroscopic notation. Okay? So using a set of numbers and letters, we will be able to arrange electrons of a particular atom in any elements, and in atoms of any elements there. So we need to understand, for a given element there, we need to understand how are those electrons distributed. And remember the quantum theory, and Niels Bohr came up with the planetary structure of the atom there, and he was so excited, and when he proposed the structure and used hydrogen as an example to do his calculation, and we find out, the line emission spectrum that we observed in the laboratory actually fits the calculated pattern. So when people get all excited, now we know how the electrons are being distributed. But unfortunately, that theory only worked with hydrogen, or a species with only one electron. But in that case, we have elements of 118 of them. They all have more than one electron. Hydrogen is only one with one electron in there. Okay, so we need to know the electron configuration or spectroscopic notation for each of the elements, so that we understand how, beyond that one electron, how are the other electrons distributed, and what are the relationships. Okay, so in this case, so why is the electron distribution important? Because it gives you the detail about how the electrons are distributed and around the nucleus of an element, and that determines the chemical properties. Okay? And chemical behavior of an element solely depends on how many electrons we have, and how many, what we call the valence electrons we have. Okay? So the valence electron is what determines the chemical property. how do you define valence electron? How do you define core electron? It's something that we want to look at in the in this particular chapter. And again, going back to that analogy of using the postal address to identify you, when we try to locate the electrons there, well, we need to know the energy level, the N value. We need to know the sublevel, the L value, and we need to know the ML value, the orbital. The region in space where an electron in a given subshell, we can find, we can actually find, once we know those numbers there, once we know that information, we will be able to identify where the electrons are. So when N equals 1, there is only one sublevel, S. And there is only one orbital, ML equal to 0. Okay. When N equals to 2, there are S and P. So you have 2S and 2P. Well, for 2P, you have PX, PY, and PZ. Okay. So you have 2 sublevels, a total of 4 orbitals there. Okay. So for N equals to 3, well, you have 3 sublevels, a total of 5 plus 3 plus 1. That's a total of 9 orbitals there, and so on and so forth. So that's what we talked about in chapter 7. Okay. And the number of orbitals that we have there, S has 1, P has 3, D has 5, F has 7, G have 9, and you can predict that H is going to have 11 orbitals there. Now we don't really need to go that high, because if each orbital can accommodate 2 electrons, and when N equals to 7, you could have 7 possible sublevels. And each possible sublevel will have different number of orbitals there. We will have a hotel large enough to accommodate all of the 118 electrons when you have N equals to 7. When you go to G and H, you will have enough rooms to accommodate all the electrons there. So this is another slide that reviews the basic shape of the electron using the first 3 principal quantum number, N equals 1, 2, and 3. So N equals to 1, there is 1 orbital. N equals to 2, 1, 2, 3, 4, total of 4 orbitals there. N equals to 3, 5 plus 3 plus 1, total of 9 orbitals in there. Okay, so that's how they are oriented in the space there. I can't pronounce that word there. So how they are aligned, and that's probably a better word to describe the spatial relationship of different orbitals there. Okay, so here, what we need to discover here, what we need to continue in our discussion is that once we identify the orbital, well, it's like we identify the room number in a hotel. How many electrons can we put in there? Well, and each orbital can accommodate a maximum of 2 electrons. So you don't want to overcrowd the hotel room, and you can only put 2 people in there. So in this case, when we say no more than 2 electrons can occupy the same orbital, and if you don't have to have double occupancy, if you only have 1 electron, well, you put that electron in the orbital there, and that's, well, the room is, you know, the electron has itself, and all the room, all the space to itself. Okay. But if you do have 2 electrons in the room, to give each electron enough elbow room there, and then those 2 electrons will have to spin on the opposite direction. Now this is known as the Pauli exclusion principle. You can only have up to 2 electrons there. You can have 1, you can have 2, but you cannot have 3. When you have 2 electrons in a room there, and those 2 electrons will have to spin on the opposite direction, which is the last quantum number, ms, electron spin quantum number. Okay. Positive 1 of 2, negative 1 of 2. And that number is